Good morning students, this is Latif sir. In this video today I'll discuss about group 17 and group 18. So group 17 elements are also known as halogens and the elements are fluorine, chlorine, bromine, iodine and astatine. These are group 17 elements and their general electronic configuration is NH2NP5. This is the general electronic configuration of group 17 elements. Okay, so and their common oxidation is generally all elements of group 17 elements can show -1 oxidation state. Okay, and fluorine only can show only -1 oxidation state, and other halogens like chlorine, bromine, iodine, these halogen elements can show positive oxidation state also, like chlorine, iodine, these elements can show +1, +1, +3, +5, +7 oxidation state also. Okay, so their electronic configuration NH2 NPC NP5, and their common oxidation state I have already told. Fluorine can only show only -1 oxidation state, and the other halogen can show positive oxidation state such as +1, +3, +5, +7. Okay, so group 17 elements, their general properties are given. Atomic and ionic radius, you know that down the group atomic and ionic radius increases, fluorine is the smallest, and ionization enthalpy also given, electronegativity, these are general properties. Okay, now see bond dissociation enthalpy of different halogen. Okay, so halogen, you know, halogen molecules are diatomic, that is F2, Cl2, Br2, I2, these are halogen molecules. Okay, and bond dissociation energy or bond dissociation enthalpy of different halogen elements is, the order is Cl2 greater than Br2 greater than F2 greater than I2. Okay, so as the size increases, as the size of halogen increases, bond dissociation energy of the halogen decreases. As the size of halogen atom increases, bond dissociation energy decreases. Okay, but here one point you have to remember, that bond dissociation enthalpy or energy of chlorine is more than fluorine. Why? Fluorine is the smallest. Okay, but so bond dissociation and energy of fluorine should be more than chlorine, but bond dissociation energy of chlorine is more than higher. Why? Why? This is because there are large large lone pair repulsion between two fluorine atom. Huh. Due to smaller size of fluorine, and you know, three lone pair electrons are present on fluorine, each fluorine atom, and due to large electron lone pair repulsion between two fluorine atoms, the bond dissociation energy of fluorine is much less than bond dissociation energy of chlorine. Okay, and color is given. All halogens are generally colored. Okay, now see oxidizing power of different halogen molecules. All halogens are strong oxidizing agent because they have strong tendency to accept one electron. Okay, and oxidizing power of different halogen elements is in the order F2 greater than Cl2 greater than Br2 greater than I2. So oxidizing power decreases down the group. Oxidizing power of fluorine F2 is more than Cl2 than Br2 than I2, and reactivity towards with hydrogen. Okay, all halogen forms hydride like HX. Okay, so in different halogen form different hydride like HF, HCl, HBr, HI. Acidic, now see acidic strength of different hydride of group 17 element, that is acidic strength of HF, HCl, HBr, HI. The acidic strength increases from HF to HI. Okay, this is because the bond length increases from HF to HI, and the bond become weak in case of HI, and the bond is strong in HF. That's why HI can release H plus ion more easily. So so acidic strength is in the order HF less than HCl less than HBr less than HI, and stability order is HF, just the reverse is the stability order. HF is more stable than HCl, which is more stable than HBr, which is more stable than HI. Okay, Now boiling point of different hydrogen halide, that is HCl is less than HBr less than HI less than HF. And boiling point of HF is most is highest. This is because HF can form intermolecular hydrogen bonding. Generally boiling point increases with increasing molecular rate. Okay, so HF molecular rate of HF is least, but molecular rate of HI is highest, is maximum. Okay, so boiling point generally should decrease from HF to HI, but due to presence of strong intermolecular hydrogen bonding in HF, boiling point of HF is maximum. Okay, so boiling point order is HCl less than HBr less than HI less than HF. Now ionic character, percentage of ionic character is more in HF, and it decreases from HF to HCl to HBr and HI. And reducing power of different hydrogen halide, reducing power of HF is less than HCl, which is less than HBr, which is less than HI. Okay, now see important compound, interhalogen compounds. What is interhalogen compounds? Okay, interhalogen compounds are binary compounds of two different halogen, like ICl, like IF7. So binary compounds of two different halogen atoms of general formula X, X prime, N, where these are called interhalogen compounds, where N is equal to 1, 3, 5 or 7. That is ICl or IF3 or IF7, like this. Okay, all these interhalogen compounds are covalent compounds. Okay, so interhalogen compounds are found by combination of two different halogen atoms, and they have general formula X, X dash N or X, X prime N. Okay, and value of N is 1, 3, 5 and 7. And all interhalogen compounds are more reactive than halogen, because the X, X dash bond is more polar than X, X bond. The bond present in the bond present in interhalogen compounds is more polar than the bond between two halogen atoms, same halogen atom. That's why interhalogen compounds are more reactive than halogen. And all interhalogen are diamagnetic. Okay, and their melting point is little higher than halogen. And example of different interhalogen compounds are given: XX dash type interhalogen like CLF, VRF, VRCl, ICl, IBr, IF. These are all linear shape interhalogen compound. And XX3 prime or XX3 dash type interhalogens are ClF3, BrF3, IF3, ICl3. These are XX dash 3 type interhalogen compound, and all these are bent T-shape structure. And X5 dash type interhalogen compounds are ClF5, BrF5, IF5. All these are square pyramidal shape. Okay, and interhalogen compounds of the type XX-7 is IF7, and the shape of IF7 is pentagonal bipyramidal. So example of different type interhalogen compounds, and their shape also given here. Okay, and now see oxoacid of halogens, not given in the syllabus, not required. And in the syllabus, compounds of halogen, that is chlorine. Huh? Chlorine, about chlorine, preparation of chlorine gas, Cl2 gas. Chlorine means Cl2 is given in your syllabus. Okay, and preparation reaction of chlorine also given. So preparation of chlorine gas, you can prepare chlorine gas from MnO2 and HCl. When MnO2 reacts with HCl, hydrochloric acid, you will get MnCl2, H2O and chlorine gas. Okay, one more reaction, reaction between KMnO4 and HCl. 2 KMnO4 plus 16 HCl implies 2 KCl plus 2 MnCl2 plus 8 H2O plus 5 Cl2. So using this reaction you can also prepare chlorine. Okay, Decans process, electrolysis, electrolytic process of preparation of chlorine is not given in the syllabus. And laboratory preparation you have to read. Laboratory preparation, first laboratory preparation by heating manganese dioxide. I have already told this reaction by heating manganese dioxide with concentrated hydrochloric acid. Okay, Chlorine is prepared easily by heating manganese dioxide with concentrated hydrochloric acid, and the reaction is MnO2 plus 4HCl implies MnCl2 plus Cl2 plus 2H2. This is laboratory preparation of chlorine gas. One more reaction is also given. A mixture of common salt like NaCl and concentrated sulfuric acid is used in place of HCl. Okay, so when NaCl combine is heated with MnO2 in presence of concentrated sulfuric acid, you will get chlorine gas. So the reaction is 4NaCl plus MnO2 plus H2SO4 implies MnCl2 plus 4NaHSO4 plus 2H2O plus Cl2. So these are two main preparation of chlorine gas. Now see reaction of chlorine. Reaction of chlorine, action with alkalis, that is NaOH. Okay, reaction of chlorine, action with alkalis. The reaction of chlorine with strong alkalis such as sodium hydroxide or potassium hydroxide depends on the temperature of the reaction. The reaction of chlorine with strong alkalis such as sodium hydroxide or potassium hydroxide depends upon the temperature of the reaction. So first, in cold condition, chlorine reacts with strong alkalis to form chlorides and hypochlorites like NaCl and NaClO. In cold condition, when chlorine reacts with sodium hydroxide NaOH, you will get sodium chloride, sodium hypochlorites NaCl, NaClO and water plus H2. So the reaction is 2NaOH plus Cl2 implies NaCl plus NaClO plus water. Okay, sodium chloride and sodium hypochlorite. In hot condition, chlorine reacts with strong alkalis. Like NaOH or KOH to produce chlorides and chlorates. Sodium chloride and sodium chlorate. Like the reaction is 6NaOH plus 3Cl2 in hot condition. Okay, 6NaOH plus 3Cl2 implies 5NaCl plus NaClO3 plus 3H2. Sodium chloride plus NaClO3, it is sodium chlorates NaClO3 plus 3H2. So these are important reaction of chlorine, reaction with sodium hydroxide. Okay, and action with ammonia is also given. The reaction of chlorine with ammonia depends upon the proportion of the reaction. The reaction of chlorine with ammonia depends on the proportion of the reaction, such as if ammonia is excess, then you will get nitrogen. The reaction is 8NH3, it is NH3, mistakenly it is written 8NH8, it is actually NH3. So 8NH3 plus 3Cl2 implies NH4Cl plus nitrogen. When ammonia is excess, 8NH3 plus 3Cl2 implies 6NH4Cl and nitrogen N2. But if chlorine is excess, then you will get nitrogen trichloride NCl3. Okay, so NH3 plus 3Cl2. If chlorine is excess, then you will get NCl3 plus 3HCl. Okay. So all the preparation and reaction of chlorine is important. Okay, now see group 18 element, that is inert gases or noble gases. The elements are neon, helium, neon, argon, krypton, xenon and radon, and their general electronic configuration is NH2NP6. Okay, NH2NP6, and they have fulfill electronic configuration, and that's why noble gases are very inactive, very inert. Okay, they do not form compounds with any other element generally. Okay, but xenon can form compound with fluorine or oxygen. Now see properties of group 18 elements. Ionization enthalpy, you know that very high ionization enthalpy because of their stable electronic configuration. They have field electronic configuration. Okay, electron gain enthalpy and melting point, boiling point, these are general properties given. These are not important. Now see the importance of xenon, compounds of xenon. This is important, you have to read. Compounds of xenon can form some compounds with fluorine and oxygen. Xenon form 3 fluorides like XeF2 xenon, XeF2, XeF4 and FCX6. Okay, these are compounds of fluoride of xenon. Okay, when xenon combine with fluorine, in nickel tube at 673 Kelvin temperature, you will get XeF2. The ratio is 2 is to 1 ratio. In 2 is to when xenon combined with fluorine in 2 is to 1 ratio, then you will get XeF2. When xenon combined with fluorine in 1 is to 5 ratio, in nickel tube at 673 Kelvin temperature and at 5 to 6 atm pressure, you will get XeF4. Okay. Similarly, when xenon combined with fluorine in 1 is to 20 ratio in nickel tube at 673 Kelvin temperature and in presence of very high pressure 50 to 60 atm, you will get XeF6. Okay, so these are compounds of xenon. Preparation of this compound is given. Okay, and xenon fluoride of xenon, that is XeF2, XeF4, XeF6 react with fluoride ion acceptor like PF5, SBF5, ASF5 to form adducts in which the fluoride change to cationic species, whereas the fluoride ion acceptor from fluoroanion. Like when XeF2 combine with PCl5, it will the product will be XeF and PF6 minus, XeF plus and PF6 minus. Similarly, when XeF4 combine with SBF5, you will get XeF3 plus and SBF6 minus. Okay. Now see oxide of xenon. Oxide of xenon. The oxide and oxyfluoride of xenon are obtained from fluorides. Xenon trioxide can be obtained by the hydrolysis of XeF4 or XeF6. Okay, so preparation of xenon oxide like XeO3. So when XeF4 reacts with water, hydrolysis reaction of XeF4 gives XeO3, oxide of xenon. Okay, so 2XeF4 plus 3H2O implies Xe plus XeO3 plus 6HF plus F2. Similarly, XeF4 plus 3H2 implies XeO3 plus 6HF. Okay, so these are the preparation of xenon oxide. And now xenon oxyfluoride like XeOF2, XeOF4, these are xenon oxyfluoride. The oxyfluoride of xenon, namely xenon oxydifluoride XeOF2, xenon oxytetrafluoride XeO4, are also obtained by partial hydrolysis of XeF4 and XeF6 respectively. Here given preparation of xenon oxyfluoride XeOF2 and XeOF4 by partial hydrolysis of XeF2 and XeF6 by partial hydrolysis of XeF4 and XeF6. Okay, so when XeF4 hydrolyzed partially by water, then you will get XeOF2 plus 2HF, and when XeF6 partially hydrolyzed by water, then you will get XeOF4 plus 2HF. And at the last, structure of xenon compounds, very important. Hybridization of the central noble gas and noble gas element and type of hybridization and shape of this compound, you have to remember, very important. In this tabular form, given shape of different xenon fluoride compounds are given, and their hybridization also given, state of hybridization. You can see in xenon difluoride, in XeF2, oxidation number of xenon is +2 and state of hybridization is sp3d, and the structure is linear. In XeF4, the oxidation state of xenon is +4 and the hybridization is sp3d2 and the shape or structure is square planar. In XeF6, the oxidation state of xenon is +6 and the hybridization is sp3d3 and the shape is distorted octahedral. The shape is distorted octahedral. In XeOF2, the oxidation number is +4 and the hybridization is sp3d and the structure is T-shaped. In XeOF4, the oxidation state is +6 and the shape is and the hybridization is sp3d2 and the structure is square pyramidal. And in xenon oxyfluoride XeOF3, the oxidation state is +6 and the hybridization is sp3 and the shape is pyramidal. So this shape, hybridization, oxidation number, all you have to remember. Okay, and now at the last, structure of different xenon fluoride, xenon oxyfluoride, all are given here. Okay, you have to draw this structure, you have to practice. Okay, and use of noble gas here given. Helium is used in nuclear reactor as cooling gas. Neon is used in discharge tube, uh, which is the reason behind the reddish orange glow produced by neon light. And xenon and krypton find their application in photographic flash. So these are use of some noble gases. Okay, and this chapter is completed. Thank you, students.